Hello and welcome to our next set of college algebra notes. We're on Unit 3, Outcome 2. So last section we introduced inverse functions and one-to-one functions, and I told you how we're going to introduce new functions and then talk about their inverses. So today in this section we're going to introduce those new functions, which are exponential functions. And then in the next outcome, so the next set of notes, you'll see us talk about the inverse of these exponential functions. So exponential functions. You've heard of exponential functions before, most likely, because we use exponential functions all over the place in real life. We use them in lots of fields of science. They're used in music. They're used in population growth, all kinds of different things. Probably the main way people think of these is when it deals with like the populations of viruses or animals and how those increase over time, doubling. We'll see a lot of examples in this set of notes working with money and finances. So we'll see how financially we use these exponential functions a lot. But what makes it an exponential function? What's special or different about exponential functions? Exponential functions, the big difference here is that the variable x is in the power. So instead of the base being x and then having a different power, so we like with our x squared or x cubed or x to the fourth or the square root or cube root, all that stuff, we'd have x in the baseline, and then we'd have like the power would be what makes it special, what makes it, defines it. Here, the x is the power, the variable is the power. And that's what is going to make an exponential function different from other functions, is the x, the variable, is in the power. When you're working with exponential functions, the base, so the number that you're taking to that power, always has to be a positive constant and not 1. We don't like to work with negatives because if you take a negative number to a power, you end up with flipping back and forth between positives and negatives. Think about it. If you have -1 to the second power, well, the second power would make it a positive. If you have it to the third power, you have a negative. So working with negative numbers to powers, you end up with this function that jumps up and down between positive and negative. It makes it really confusing. And we don't like to work with 1, because if you let the base be 1, well, 1 to any power is always going to be 1. 1 to the first is 1, 1 to the 10th is 1, 1 to the millionth is 1, because 1 times 1 times 1 just gives you 1. So we're only going to use positive numbers other than 1. So they're going to be bigger than 0, positive, and they have to not be 1. And that's what's going to be basis. We can write this in function notation, so we can write f of x, or we can write y equals b to the x. So either way is fine. We'll just use this function notation because these are functions. These exponential equations like this with some base that's positive to the power x, they are functions. We'll see that when we graph and all that. X can be any number as long as it's a real number. So when you're working with these kind of things, you'll actually have a lot of problems where you take numbers to some weird powers. So the first couple questions here on the notes just show us doing that a few times. So they have us taking 3 to the 3.4 power. You're just going to use a calculator or stuff like this because you're not going to be able to get that really by hand, not at least in this course. So we'll take 3, and then we'll use the power button, which is this up arrow here, power 3.4, and that would give us the result 41.8998. That's what we get, 41.8998. But it does say to run to 3 decimal places, so you want to make sure you round these appropriately. So this would tell that 9 to go up, which actually would carry over to this one, which carried to this one. It ends up giving us 41.9. You can put the zeros there if you want 3 spots, but that's what it would round to. So you can have decimal powers, you can have root powers, like actually like 5 to the third. So we'll do 5. Again, we're using the power button here, so we'll use the power button. And then I want square root, so I'm going to hit second and do the square root button right there. And then I got 3 inside that root. So I have 5 to the square root of 3, and that would be about 16.242 is what this rounds to. So round away 3 decimal places, 16.242. So again, you can have weird powers because anything can be a power as long as it's a real number. No imaginary powers, but anything real could be a power. Last one here, we have e. I just want to point this out to you. So this e, it's a number kind of like pi. If you were, if you've ever celebrated Pi Day, stuff like that, it's about 3.14, but it's a decimal. It goes on forever. It never repeats. E is a number like that. We'll talk more about what e is later, but it's a number that, like pi, that's a decimal, goes on forever. If you work with it, a lot of times you could round it, but e we try to avoid rounding because usually with powers, if you round, that ends up making the final answer too much rounded. It doesn't work very well. So to do e, we're going to use a button on our calculator. So we use the e to the x button on your calculator. If you try and round e, then you're going to end up with an answer that's not going to be, it's going to be so rounded it's not going to work. So on your calculator, you should have a little button like this where it has e to an x, especially if you have a T84 like mine. I'll have to use the second button to do that, so I'll hit second, and then this button gets that e to the x. And then by default, it always puts it with a power because they usually expect you to work with e to a power. So if what you're doing is using a power, like here, that's fine. So you just put 2.3. If you ever have to use just e the number by itself without a power, you just put 1 for the power, because e to the first is just plain e. So this one gives us 9.97, which makes sense because e is about 2.7, so not quite 3. So if you take it to the second second power, it's about kind of like squaring it, so you should get a value about 9, because 3 squared is 9. So that makes sense. It seems feasible. Yes, the answer to this would be 9.974. So 9.974. And so the big thing I want you to know for now is just if you're working with e in this section at all, make sure you're always using the button on the calculator. You don't want to round that. If you round e to like 2.718 or whatever, it's going to be too rounded. You end up with answers that are really off. So you always want to use e, the button on your calculator, not the rounded version. I know pi, you don't have to take very many decimal places in it. Still works, but e, because of how we use it, that's not a good idea. Don't want to round it. Okay, let's graph a couple of these exponential functions. Your homework has you do it with the table, so we'll just go ahead and make a table. Remember those t-charts you've seen before in this class or in other classes, where you have your answer, your input x's. Your output can either be y or f of x. I'm just going to put f of x because that's the result. So we put in something for x, and then we get a result out, which is y or f of x. And I can put any numbers I want in here. I'm just going to put a couple different numbers so I can see what it does. I usually like to put like 3 to 5 numbers in here. The more complex the shape, the more numbers I'll put in. So I might start with easy stuff like 0, 1, 2. Also, it's always good to see what happens on the negative side. So I might put in some numbers like -1, -2. There I've got 5 numbers. This is probably good enough to kind of figure out what's going to happen. So each one of these I'm going to plug in here and see what happens. So I'm going to do 2 to the 0. Well, 2 to the 0 is just 1, right? Because anything to the 0 power goes back to 1. So this is 1. Next one I have 2 to the first. Well, that's just 2. 2 to the first is just 1, 2. 2 squared, so 2 to the second, which is 4, because 2 squared means 2 times 2, so I get 4. 2 to the -1, remember the negative power, you put it on the bottom of the fraction, so this becomes 1 over 2 to the first, or just 1 over 2, so it becomes 1/2. And 2 to the -2nd, so then I put it on the bottom, so I put 1 over 2 to the second, and then 2 seconds is 4, so I get 1 over 4, so I get 1/4 for that one. So do it by hand, not too big a deal. It's a good way to do it. You just are putting these different x's in for the power, because the power is what's changing, and then see what results you get out. And you have to remember your properties, your rules about like negative powers, anything to the 0 power is 1, and then it can help you get these points, and you can graph it. So if I graph this, I've got 0 is 1, 1 gives me 2, so 1 gives me 2, 2 gives me 4, so 2 gives me 4. -1 gives me 1/2, so -1 gives me 1/2. -2 gives me 1/4, so -2 right here would be like 1/4. And you can see that as it goes to the right, it actually curves upwards pretty steeply. And then as you go to the left, it's going to level off. And it's going to get lower and lower and lower. It'll never quite reach 0, because you can't take a positive number to a power and get 0. You can't take a positive number to a power and get a negative. You also notice that this is never going to give us a negative. It can just get really small. That's all it can do. It can't get a negative. It can't get 0. But it can just get really small, closer and closer to 0. That's all it can do. So that's how exponential functions tend to look. And we could do that using, finding those points by hand. You could also just do this with a calculator. So if you want to get the graph or the table, you could go to the y equals, type in that 2 to the x, 2, 2, use your power button, the x for the value and the power, and you can graph it so you can see what it looks like, and you can see how it's really level and then it starts climbing upwards once you get past 0 going to the right. It's when it really climbs up. And then you can also see if you hit second and then graph, so you get the table. You can see the table values there. So the 0, 1 we got, the 1, 2, the 2, 4, the 3. We didn't even get the 3, 8, but that would be there. -1 is 0.5. You'd have to recognize that's a half. -2 is 0.25. That'd be 1/4. So those ones are a little bit harder with the decimals. That's one reason it's nice to do it by hand, because it helps you get the fractions instead of getting the decimals. But yeah, that's the idea. This is 2 to the x. This is what it looks like. Let's do one more. We're going to do 2/3 to the x. Again, the base can be any number as long as it's positive and not 1. So it can be big numbers, or it can be small numbers. It just has to be a positive number, no negatives, and it can't be 1. So on this one, again, we're going to make our t-chart. We have x here. We have 2/3, or sorry, f of x. I don't know why it's coming to 2/3. 2/3 is what we use to get f of x. Again, you could put y if you prefer. So that's our going to be a result. So input, output. So first, if I do 2/3 to the 0, because we'll do like 0, 1, 2, -1, -2. Those are good numbers. We'll do the same set. So 2/3 to the 0, anything to the 0, still 1. So it's going to give us 1. And do 2/3 to the first, which gives us 2/3. The next one is 2/3. We're going to do 2/3 to the second. Remember that when you square a fraction, you square both the top and the bottom. So end up with 2 squared is 4, 3 squared is 9, so this becomes 4/9. Next one, we have 2/3 to the negative first. Remember with a fraction that when you have a negative power, you end up actually flipping the fraction upside down. So this becomes 3/2. So we get 3/2 for that part. Next one, we do 2/3 to the negative second power. So we flip it over, and then we also square it. So we're going to end up with, the 3 squared on top gives us 9. The 2 squared on bottom gives us 4. So we end up with the 9/4. It's like doing the squared one, but just flipping it over because of the negative power. So we get 9/4. Now this one is a good example of why you might do it by hand, because if you put 2/3 to the x in the calculator and try and use that for your table, so you do 2 divided by 3. You have to make sure you put parentheses around there, do your power. If you get it typed in and everything correctly, and then you use the table, you end up with something like this, where all these are going to be decimals, which they do turn into fractions. You can see from over here, but it makes it kind of hard to see the fractions from here. So this is why you might want to do this one by hand and kind of get the fractions. If you want nice exact answers. And if you're just trying to look at the graph, of course, you could just hit the graph button and see what the graph looks like. So we'll see that's what's going to look like. So if you're just trying to graph it, yeah, you can just graph that equation that we have. But if you're trying to get the table entries, I think using it by hand is probably easiest. Okay, so we got 0, 1, so 0, 1. 1 is 2/3, so it's going to be about there. 2 is 4/9, that's less than half, so it's going to be down here. -1 is 3/2, so 1, 2, 3/2. -2 is 9/4, so that's 4/4, 8/4, 9/4. And that's what we get. So it looks something like this. There we go. So this is 2/3 to the x. There's a little difference here. Instead of getting bigger, it's actually getting smaller. And then again, it's going to get closer and closer to 0. But again, you can never get 0 or a negative if you're starting with a positive number and taking a power. Because all the powers can do is they can either they can multiply times itself. They can't turn it into a negative. They can't make it 0. So they can only give you another number. It's got to have to be bigger than 0. So you can see there's a big difference here. We have two different graphs. We have the one that goes up to the right and the one that goes down to the right. The big difference being the number that we use, the base. And if you start with a base number that's big, and when I say big, I just mean bigger than 1, because anything bigger than 1 will be big, you're always going to go up. Because if you take stuff and you multiply by 2 more and more times, or even if you multiply by something like 1.5, anything bigger than 1, you multiply by a number like 1.5 over and over again, every time it gets bigger. And so as it gets bigger and bigger and bigger, it's going to climb up the curve. Versus small numbers, things less than 1, like 2/3, a half, a fourth, a tenth, those things, every time you multiply by something small like that, the number amount gets smaller. Think of your bank account. If you multiply by half, you'll have half as much money you have less money, it's getting smaller. So if you use like a half or 2/3 or something like this, every time you multiply, the amount gets smaller and smaller and smaller. And so that's why it kind of gets smaller and smaller here and levels off, because we're multiplying by that small number over and over and over again. So the more times you multiply by that small number, the further it gets to being zero, closer to zero. So that kind of leads us to the two main types of exponential functions, the two ways to look at them. And then this, table here just shows you all the information you really need to know about these exponential functions. So first off, either way, whether you're working with the big numbers or small numbers, the domain for these is always all real numbers. You can use any number for the power, right? You can use negative numbers, positive numbers. You can use any number for power as long as it's a real. So that's why the powers always take real numbers. That's their domain, all the x's. The range, so the outputs, the results, the range are all positive real numbers. So again, the range can only be positive. It's never going to give you anything 0 or below. It's only going to be positive. Domain is anything, so from negative infinity to infinity, because it goes left and right forever. And the range is just from 0 to infinity, not including 0, right? It's going to be anything above 0. The graph of all exponential functions go through the point 0, 1. So you're always going to pass through the point 0, 1, because anything to the 0 power is 1. If you put 0 for the power, that's x is 0, then the answer is always 1. It doesn't matter what fraction you start with. You're always going to have a point right here as 0, 1 for these exponential functions. So you should see that on the last two we did, that both of those had a point at 0, 1 right there, because the 0 power is 1. Okay, now if you start with a base that is big, anything bigger than 1, then it's always going to go up to the right. It's going to be what we call an increasing function. Remember when we said when you go up to the right, you're increasing? So functions like this, because the base is bigger than 1, that's an increasing function. If the base is less than 1, so if the base is between 0 and 1, then it's going to go down to the right. It's going to be a decreasing function. So a function like this is decreasing because its base is small. Anything below 1, so half, a third, a tenth, all those numbers make it smaller and smaller. For these, the bigger the big number, the steeper it is. The smaller the small number, the steeper it is. That's going to be what makes those more or less steep. A couple things to note about these. These functions, these exponential functions, are one-to-one functions, which means they do have an inverse. So they are one-to-one. They have an inverse. It's also a function. It's hard to see on here because you have both graphs, but if you just look at either of the ones I just did, you can see here that if you try the horizontal line test, it's going to pass. There's no place where you can draw a horizontal line and cross more than once. So this is one-to-one. It does have an inverse. Same thing here. If you draw that horizontal line, you're only going to cross once. So it is one-to-one. It does have an inverse. They're one-to-one. They have an inverse. And notice that they get close, but they don't quite touch this horizontal asymptote. So that horizontal asymptote, that's actually going to be the line y equals 0. It's going to be this line right here. Is our horizontal asymptote, because they don't ever quite touch the x-axis. So the x-axis, or y equals 0, is a horizontal asymptote for these functions. You always have that line to get close to on the ends, but never quite reach. Remember we said that horizontal asymptotes, it's all about what happens at the end. Well, at the end of either one of these, it's getting closer and closer to 0, but it's never going to quite reach it. I'm going to graph one more. This one, we're not going to bother with the t-chart, because now we know enough about graphing this that we can just graph it from what we know. First off, we know that it's got to have a point at 0, 1. So these always have a point at 0, 1, because you plug in 0 for the power, you get 1. So there's always going to be that point, 0, 1. Another thing we said is it has to have a horizontal asymptote. So it's going to have a horizontal asymptote right here at y equals 0. That's the line it gets closer and closer to. Here, because 3 is bigger than 0, or, sorry, not bigger than 0, bigger than 1. 3 is bigger than 1. This is going to go up to the right. So it's going to be an increasing function. So I know it's going to go like this. So on the left side, it's going to kind of get closer and closer to that asymptote. If I want a more perfect graph, yeah, I'd, figure out what negative 1, 3 to the negative 1 is, 3 to the negative 2. I'd get better values down here, but I'm just doing a quick graph. If I want more over here, I could put in powers again. I could do like 3 to the first is 3, and that'll tell me that point. 3 squared is 9, and so it's way off there. But again, if I just want a quick, easy graph, all I have to know is where the 0, 1 is. There it is. And that has an asymptote right here, and then it's going to go up to the right. And you can basically get the idea from the graph there. When you're working in MyLab, it does have a exponential tool. Be careful, make sure you're grabbing the exponential tool because there's another curve that looks really similar, has a different name. So you'll want to make sure you're grabbing the one that says exponential tool. If you hover your mouse over the button when you're graphing, it'll tell you what kind of graph it's going to draw. There's one for the quadratics, there's one for straight lines, there's one that's called exponentials. So you want to make sure you grab that one to graph this. And I think it only needs like maybe 1 or 2 points. So the 0 to 1 will probably be enough to graph it. And again, if you want a better graph of this, you can just put this in your calculator. And that would give you a much more precise with all the values. You can use the table and stuff. We're just doing it quick and easy and saying, because we know it goes up to the right, we know it has to cross 0, 1, we know it has to have a horizontal asymptote. We can get a good idea of the graph from just that. Okay, so that's exponential functions. Exponential functions have all these characteristics, all these properties, and they're important for you to know. Like I said, there's lots of real-life applications for these. If you're going into finance, you'll see exponential functions. If you're going to medicine, you'll see them because they deal with the way we deal with drugs or the way bacteria and viruses reproduce. If you're going into chemistry or physics, you'll see these in those fields. They're all over the place, really. So you will probably see exponential functions in some form in most fields that you're going to work in. Okay. Now, we talked earlier, last unit, I think it was last unit, about transformations and how you can do all these transformations to graphs. These transformations can also be done with these functions because these are a type of function. You can transform any function. And thankfully, they work the same way as always. So these aren't anything new. This is stuff we've seen before. You should remember that there's the vertical stuff. Remember that vertical things are always stuff you do on the outside. So here we're adding on the outside or subtracting on the outside. Remember that when you add on the outside, it shifts it upwards. If you subtract, you shift it downwards. Horizontal translations. So horizontal is going to be stuff that's on the inside. So here it's inside is going to be inside the power, right? So the power is the inside. And these are still going to shift, but remember that horizontal is always kind of backwards. So adding a number is going to shift it to the left. Subtracting a number is going to shift it to the right. Always feels backwards to me because the right is the positive direction, but adding actually shifts it to the left. Reflections, so if you have a negative in front of the whole expression, that's going to be a vertical shift, reflection over the x-axis. So what I like to call, vertical, because it's going to flip it upside down. And then the other one is going to be your negative on the inside, so you go negative inside the power. And it's going to reflect it over the y-axis, which I would call a horizontal reflection, because you flip it side to side. You can do stretching and shrinking. If you want to vertically stretch or shrink, you're going to put some number on the outside that you multiply by. So here we're multiplying by a big number, we'll actually stretch it, and multiplying by a number small, between 0 and 1, we'll shrink it. Horizontal is backwards, so horizontal we multiply inside, and a big number is actually going to shrink it, and a small number is actually going to stretch it. So those are the same transformations we've seen before. There's not really much different there. What I expect you to be able to do is to look at an equation like this and think about what the original equation was. Well, this one was, the original equation was f of x equals 3 to the x. So you look at that and you see the differences here, what's changed, and then those should tell you what transformations you have. So here you should be able to see that there's a negative in the power, and there's a minus 1. So those are going to be the two transformations, the negative in the power, and the minus 1. So first off, the negative is inside the power. So since we have a negative on the inside, it's a reflection over the y-axis. So this is a reflect over y-axis, or what I would call horizontal. Because when you reflect over the y-axis like this, you flip it horizontally. The other thing we see here is that minus 1, it's not inside because it's not in the power, it's outside. So we have a subtract 1 outside. and subtracting 1 on the outside, that's going to be a shift, because subtraction is always a shift when you subtract a number. And since it's outside, it's going to shift it down. So that's going to be a shift down by 1, or a translation is a fancy name, but it shifts it down, it brings it down 1. So I think about my original function, 3 to the x, looks like this. And I think about my transformations, make sure you do it in order. Remember, you always start with any horizontal shifts first, which there are none. Then you do your reflections and stretches in the middle, so I'll do this one first, actually. And then the last thing you do is any vertical stretches or vertical shifts. So that'd be the order. We'd start with this one and then do that one. And what I like to do is I first off think about how this is going to affect my asymptote. Because when you're trying to draw this, it's good to know where the asymptote ends up. So if I think about it, I start off with an asymptote right here at y equals 0, right on the x-axis. First thing I do is reflect it over the y-axis. If I flip it over, well, if you take this infinite line and flip it over, it's still the same infinite line. It doesn't matter if it's flipped over. So it's still going to be right there. Then we shift it down 1. So it's actually going to move downwards 1. So this is where it's going to end up. It's going to end up down here at y equals -1. So now I know that's the line I'm going to get close to. I'm going to get close to that one at the end. Next thing I do is I usually like to just work with some of the points I know. Like I know there's got to be a point to start with at 0, 1. So I would like start with that point and think about reflecting. Well, if I reflect over the axis, it stays there. And I shift it down 1, so it's actually going to end up here. So there'll be a point there. We did kind of think about how there's a point at 1, 3. So we're going to look at that one and say, okay, we have a point here at 1, 3 to start with, but we reflect it. So we reflect it, goes over here, and shift down 1, it's going to end up right here. So that point that was 1, 3 got flipped over and shifted down. And that's enough. Now I know that I can see because it used to go up to the right, now it's going to go down to the right because it got flipped over sideways. And it's just going to be lowered a bit. So it's going to look like this. It's going to go up to the left, and on the right side it's going to lower out and kind of get closer and closer to 0. So you can see how that is flipped over. It's flipped over sideways from the original graph. That's also lowered a little bit. Now, you probably won't have to do this quite as much by hand. I know sometimes they do just give you a single point and ask you to do the transformation, so they might do that. But the big thing is identifying those transformations. You should be able to point out, okay, the negative here is going to be a reflection over the y-axis, so horizontal, and the -1 there is going to shift it down. So that's your transformations. Okay. Let's do one more. This is the same original 3 to the x, right? So you can see how there's 3 to the x in there. But again, this has a couple transformations going on. It has the minus on the outside, and it's got the +1 on the inside. So I want you to be able to look at those and think, okay, what do they do? Negative on the outside, so we have negative outside. Remember that a negative on the outside is going to be a flip or reflection over the x-axis. So this is reflection over x-axis, or vertical reflection. So let's go flip it upside down this way. Next thing we have is that +1. This is on the inside now, not the outside. So we add 1 inside. And when you're working inside, you're doing horizontal. So this is going to be a horizontal shift. But since it's on the inside, instead of going to the right, it's actually going to the left. So we're going to shift to the left 1. So to make this drawing, we're going to start back with our original 3 to the x again, which is this original function. It's going to look like this to start with. And then we'll do all those transformations where reflect it and shift it. Again, I like to think about the asymptote first, kind of helps me figure out what's going on. So if I start with my asymptote here, I say, okay, first off, reflect over the x-axis. Well, the line's in the middle, so it's not going anywhere when you reflect it. And then it shifts left 1. Well, if it's an infinite line and you just move over the one, it doesn't really go anywhere. So it's still going to actually stay in the exact same spot. This one, the line's going to be right there. It's going to be y equals 0. So this one, the horizontal asymptote doesn't change. It's always nice to know where the horizontal asymptote is. Next thing, I'm probably going to use that 0, 1. Nice point to think about. So I had 0, 1 right here on my original graph. There's that point 0, 1. I'm going to do my stuff. I should make sure about order. With this one, notice that my first thing I'm going to do is actually going to be my horizontal shift, because you always do horizontal shifts first, and then I'm going to reflect, and that'll be the order. Remember that we start with horizontal shifts, do any reflections or shrinkings, stretchings in the middle, and then we do the vertical shifts last. So horizontal shift I do first. So 0, 1 go left 1 right here, And then reflect over the x-axis, so it's going to come down to here. So that'd be that point. So instead of 0, 1, it'd be down here. And we just saw 1, 3 was a point. So if I take that point and I shift it left 1 and reflect over the x-axis, it ends up down here. So what you can see is this one is going to go downwards like this, really steeply, and this side is going to get closer and closer to 0 like that. So you can see what this one looks like is it's the same graph flipped upside down and shifted to the left a little bit. So you can see how it's getting further down before it crosses this middle. Here it only crossed at 1, but here it's going all the way to 3 first because it got shifted to the left a little bit. So that's transformations. Again, I want you to be able to recognize the transformations so you're ready to do them. You should be able to look at what's added in here. You know, again, we started with 3 to the x, and then we added in these other things. You should look at those negatives and those adding 1, and those should tell you what transformations happened. Okay, I want to show you one more transformation, but this one we're going to work with the e to the x, which we do call the natural base or the natural number. Those are kind of two common names for it. So before I work with it too much, I want to introduce where it came from. Why do we have this e, this natural number? What happened is the mathematicians found themselves working in situations where they're working with this expression right here. So this expression is important. It shows up in lots of mathematics, where you take a 1 plus 1 over a number to the same number power. So if you do like 2, you have 1 plus 1 half to the second power. Or if it's 5, you're doing 1 plus 1 fifth to the fifth power. Or 10, you do 1 plus 1 tenth to the 10th power. And then they found themselves wanting to make the n, the number, get as big as they could. So they said, what happens is n shoots off to infinity. And what they found is that it does approach a specific number. Now, it's not a nice number. It's a decimal number. It does go on and on forever. You know, here, this is kind of an approximation. It's about 2.718. But again, the real number goes on forever. It's like pi. You know, it doesn't end. It never repeats. It just goes on and on forever. So e is the number you get close to, you approach, if you let this expression, if you let n get bigger and bigger and bigger and bigger. That's where e comes into play. So we actually graphed e to the x right here for us. This is what e to the x looks like. It's right here. E is a big number, so it does go up to the right. It is a little bit smaller than 3, so it's not quite as steep as 3. It's pretty close. It's bigger than 2, so it's more steep than 2 to the x. Because here it's a little closer to 3 to the x than it is to 2 to the x. It does still have a horizontal asymptote. Right there at 0. That's kind of what e to the x looks like when we graph it. So e, it's called natural number because it just naturally shows up in all these expressions. It has a lot of situations where you end up using it for a power. We'll see one of them in the set of notes, but it shows up all over the place in other situations. So you should be able to work with e to the x and even transform it. So this is what they're doing here. They're taking that e to the x function and they had some transformations. So if you notice here, we have a plus 1 on the inside and a minus 2 on the outside. So each one of those gives it a transformation. So we can see that the plus 1, so plus 1 inside, that's going to be a shift because adding or subtracting is always shift. If it's on the inside, it's going to be a horizontal shift. So it's going to be a horizontal shift. And because we're adding 1, remember that the inside stuff's backwards, so the adding 1 actually takes you left. So this would be horizontal shift left 1. The other one, the minus 2 on the outside, since it's a minus 2 outside, it's going to be a vertical shift. So it's a vertical because it's on the outside. Always outside is vertical. And vertical does what you expect. So subtracting 2 is just definitely going to move it down 2. So we're going to take this original e to the x function graph and we're going to do those two transformations to it. So we always do our horizontal shifts first, our vertical shifts last. So that's the order. So I'd start off with my asymptote. So I'd have an asymptote at y equals 0 as originally. And so then if I do my shifts, well, horizontal shift's just not going to affect it, but a vertical shift is going to move it down 2. So it's going to be moved down 2, it's going to be down here. So this is going to be our asymptote, sorry, negative 2, because it got moved down 2. So y equals negative 2 is going to be a horizontal shift, asymptote, so it's going to get closer to that. Also, we start off, we always have that 0, 1 point, so if we take this and we shift it to the left 1 and down 2, into the point there, If I had the first, so if I do like 1, that would give me E, would be, so 1E would be a point on this graph. So at 1, it should be about 2.7. But here, if I shift it to the left 1 and down 2, it's about there. So instead of being at 1, 2.7, and the left 1, down 2, it's up there. So this is what it looks like. It's going to go up to the right. Again, this isn't perfect. If I wanted a better graph, you could just type this in to get like a perfect graph. But I just want to be able to do the quick transformation. And again, on the homework, a lot of these, you'll probably mostly just be identifying what transformations occurred. You should be able to identify the +1 means a horizontal shift because it's on the inside. The -2 is a vertical shift because it's on the outside. This is what that would look like this. And this isn't a perfect curve because I hand drew it, but the idea is it should still go up to the right because we didn't do any reflections. We just did it moving to the left and down a bit. And so that's why it's here versus what it looked like originally. So that's kind of the main ideas of this section. You should be ready to work with exponential functions. You should know that exponential functions are where you're changing the power and you're getting different values. The base should always be a real number. The last thing I want to show you is one of the big applications of this. This is in finance. One of the big applications of these exponential functions is in finance. And it's when we deal with what we call compound interest. Simple interest, which I believe we mentioned before, is when you borrow money and you say I'm gonna borrow this money, or you loan money, whichever end you're on, and you say, okay, but we're gonna charge interest. So when you pay back the money at the end, you have to pay back some interest as well based on how long you borrowed the money for. And it just comes on that original amount. Now, over time, people stopped and said, well, wait a second. If I loan someone money for 5 years and they pay me interest, and then someone else 5 years and they pay me interest, I make more money than if I loan the first guy the money for 10 years and they pay me interest. Because after 5 years, I've got some interest and I actually have more money already to loan out for the second guy. And so they figured that out. So then they figured out that one of the ways to make more money by loaning money or investing money is to charge interest more than just at the end, if you do it like every year. So what happened is they do this calculation here, where they start off and say, you have your balance A, so how much money you'll have at the end is the balance A, will be based on your principal P, that's how much you loan out, so if you're investing, this is how much you invest. And then you have your interest rate, so how much the interest rate is, and then the time, that's the number of years you loaned it out for. And they say, okay, at time 0, so right at the beginning, the amount that you owe, that they owe you back, the amount you're going to get is going to be the same as what you invest, because you didn't have any time for the interest to happen. After 1 year, they say though, after 1 year, you'll have to take your principal, multiplied by 1, because you get your original principal back, and then also multiply the principal times the interest rate, because that'll find out how much interest you get. Because if you do principal times rate, that gives you, the interest for that 1 year. So you add those together, and you get the total amount that you should have from your investment. So if I go and I invest my money and I get, after 1 year, it's worth, the final amount A, which is the principal times 1 plus R. Well, then what they figured out is if you get your money back after a year, then you can go back and reinvest it. If you reinvest it for the same rate, all that, then you could take that new amount you have and multiply by another 1 plus R to get the final amount that you would have after 2 years. So basically what they're doing is after each year, they're saying after each year you have more money, then next year you can invest that and make more money. So people figured out pretty quickly that this is the best way to make money with investments, is where you do what they call compounding. So you're not just charging interest on the original principal that was borrowed at the beginning, but you're also charging interest on the money you had after a certain period of time. So after a year, say, okay, well after a year, now you owe me the original amount you owe me plus a year's worth of interest. So next year, when you calculate how much the interest is, I'm going to also include the money that happened after the first year. So you're basically charging interest on the interest, not just the principal. That's what makes it compound interest. It compounds because you're charging interest on the interest as well. So eventually they figured out that there's this formula. So if you're going to do, invest for 2 years, and you say every year it compounding. So this is for yearly compounding. Every year it compounds. Then you can use this formula, and you just do the principal times 1 plus R to the t power, where t is how much time you invest the money for. So let's look at the difference. First, I want to just show you real quick. I want to show you what simple does. So if you don't use compound interest, if you just use simple interest is just the the final amount is equal to the principal times 1 plus RT. So this is going to be if you're doing just simple interest. If you're not compounding, you just do the interest rate times the time, times the principal, that gives you your interest, and then the principal back, and that's the formula for simple interest. So let's do simple interest for a situation where we invest $5,000, 35 years, and an interest rate of 5.5%. Don't forget that when you work with interest rates, you always want to turn to a decimal. So my R is going to be 0.055, because you always move the decimal 2 spots to make a decimal. So let's put those in, see what the simple interest gives us. So we're going to have 5,000, 1 plus 0.055 times 35 years. And again, we don't really use this simple interest formula because most people don't charge simple interest anymore. Most people use compound interest. But this is just to show you, if you went back and did simple interest, let's look at that first. You would get this amount. So if we type that in there, after 35 years, that $5,000 would be worth $14,000, which is nice. You've made some money. That's awesome. But you'll see pretty quickly once we do compounding that that's not nearly as much as you could make if you compound. So let's do compound. If I do a compound interest instead of simple interest, then I use the formula A equals P 1 plus R to the T. And so then this one, I would have 5,000 times 1 plus 0.055 to the 35th power. Okay, so I do 5,000 times parentheses 1 plus 0.055 to the power of 35. And now it shows me that if I'd done compound interest, where every year I compound and figure out how much interest was owed after each year, and then added that back into the mix, instead of just 14,000, I make 32,000. That's a big difference, right? 14,000 to 32,000, that's more than double. So just by charging the interest periodically, every year, once a year, saying, hey, after this year, there's interest, that interest gets added back in the mix, and so now the next year you have to pay me more interest because you never paid me the interest previous year. So if you do it that way, you can see that you make a lot more money. So this is compound interest, this is compounding yearly, and this is what people do. When they invest money, they're looking for investments where it doesn't just pay the interest at the end. They expect to be paid interest throughout the life of the loan. They expect it to compound yearly. Now, eventually, someone said, "Well, why wait till the end of the year? Why not compound partway through the year? Maybe if I compound every 6 months, I can make more money." And so that is a thing. You can compound more than just once a year. So that's what the next formula is for. And that's actually why we don't use the formula I just showed you. We actually use this formula. This is the formula that's on your formula sheet. This is the formula for compound interest when you do periodic compounding. So it's not just for yearly, but it could be for semi-annually, like if you compound twice a year, quarterly if you compound 4 times a year, monthly if you compound 12 times a year. If you did daily, daily would be 365 times a year, right? You could do that. Each compounding period would be 1 day. So this formula does that. So what it does, this formula, it's very similar. It still has the P, the 1 plus R, but here they take the R and they divide it by N, where N is the number of compounding periods per year. That's what N is. It's how often do you compound. So like semi-annually, I compound twice a year. Quarterly, 4 times a year. Monthly, 12 times a year. Daily, 365. So you divide it by that because I can't charge a whole year's worth of interest every month, right? If I'm doing like monthly 12, then I can only charge a 12th of the interest because it's only been 1 month. So that's why you have to divide, because you have to say, oh, I'm not charging the whole interest amount because the interest rate is for the whole year. I'm just charging a piece of it. But then you also get to put N in the power, because now you're not just compounding once a year, you're compounding a bunch of times per year. Like if you're doing N equals 12, you're compounding 12 times a year. Every month you compound. So this formula incorporates that, how often you're compounding. The more often you compound, the more times you're going to use, multiply, because the bigger the power will be. But you're also going to be using a smaller fraction each time. So we're going to try this again, but now we're going to do it for compounded monthly. So it's the same $5,000, 35 years at 5.5%. None of that changed. That's the same principal, time, rate, which is really 0.055. But now we're going to do compounded monthly, so N is going to be 12. And we'll see how this actually makes us more money. So when you go and invest with our money, we're going to try and do it compounded more frequently because it'll make us more money. So the formula now, principal is 5,000. 1 plus interest rate is 0.055 over n is 12 to the power of 12 times 35, because that is the time here. I'm always going to put parentheses around the powers here, because some of your calculators, if you don't put a parenthesis around the power, it'll do it wrong. So it's good to be safe. I know my calculator is kind of the fancy one, because I got the nice color edition, whatever. So it'll be fine if I don't put those parentheses, but some calculators will need those parentheses. It's a good idea if you have powers with multiplication or division in them to use the parentheses. Okay, so here we have 5,000 times parentheses 1 plus 0.055 divided by 12, because it's again monthly compounding, to the power, and we do parentheses 12 times 35. So we should make more money now because we're compounding once every month, not just once every year. And we do almost a couple $1,000s more, right? So this one turns out to be $34,125 and like 33 cents. And I think it's not quite $2,000 more. I think it's like $1,600. That's $1,600 that we would have not made except for we compounded more frequently. The other nice thing is we didn't have to loan the money out any longer. We didn't have to look for a better interest rate, anything like that. All we got to do is say, okay, instead of charging you interest at the end of each year, I'm going to charge you interest at the end of each month. And by doing that, we make more money. And this is why banks nowadays, they try and do this. They try and compound more frequently. They're not going to wait till the end of the loan and then say how much the interest is. They're going to say, okay, every short period of time, we're going to calculate the interest and we'll add that back in. In fact, bankers who are really great at investing and make money with investments, they figured out, okay, the trick here is to maybe do as much as we can. Let's compound more than just monthly. And so that's why daily compounding came along. Because someone said, oh yeah, I could compound every single day. That'll make a little bit more interest. And then someone said, I want to compound more than daily. And how about every hour? And then someone else came along and said, I want to do better than that. I'm going to do it every minute. And then someone said, no, I want to do better than that. I want to make more money. I'm going to compound every single second. And you're like, is this legal? Yeah, it's legal. In fact, eventually, someone stopped and said, maybe I could hire a mathematician to make it, so figure out how to do the compounding every single moment all throughout the entire year, to never take a break. Like, I'm not going to wait a second. I'm not even going to wait like half a second. I'm not going to wait a millionth of a second. I'm just going to compound continuously, constantly throughout the year. So that this n is basically shooting off to infinity. N is going to get huge. It's going to get so big, it's basically infinite. And see if I can make more money. What's the most money I can make, basically. And so that's where we get to the next page. This is what we call continuous compounding. So continuous compounding is when you make n go off to infinity. So we want to let that n get really, really big and see how much money we can make. Now, eventually a mathematician was able to figure out how to do this. The bankers had the money, so they paid some mathematician and figured it out. So we started off with that formula with the n and stuff. Did some fancy rewrites, so we rewrote a little bit. Eventually got this n over r expression shown up a few times and replaced it with h, just have a different number. And he noted that if n gets bigger, then h gets bigger. So he said, okay, well, if I'm letting n go to infinity, I can just let h go to infinity instead. And then he saw this expression right here, which should look a little familiar. It has 1 plus 1 over a number to the same number power. If you wrote that with n's, it would be the same expression we used when we got e. He said if this number gets to go bigger off to infinity, this thing is going to get closer and closer to e. So he actually took this expression and replaced it with e, and this is the formula. So this is the continuous compounding formula. The final amount is equal to p times e to the rt. You'll notice we don't need n here because n has gone off to infinity. All we need to know is the interest rate r, the time t, and the principal p. This is the continuous compounding formula. So I'll put this on your formula sheet. You'll have the continuous compound formula, and you'll have the just the compounding formula, this one. If you had to do yearly, you just do n as 1. So if you ever have to do yearly, so we won't really put the yearly formula on here. We'll just either do compounding periodically or we'll do continuous compounding. You always know to use this formula because it will literally say the word continuously. So you'll be looking at your problem and you'll see somewhere where it says continuously. If you use continuously, then you're using this formula, and that's how you know. Okay, so we're going to do this one more time with the continuous compound interest. Still the same amount of money, right? $5,000, 35 years, 5.5%. And we're going to see how much money we can make with this investment. This is the most we can make. This is compounding as much as we possibly can. So our final amount is going to be equal to P, which is that 5,000 principal, P, times E, which is that value, that 2.718. Well, we'll use the button on the calculator to be more exact. To the interest rate R, which is 0.055, don't forget to turn it into a decimal, times the time T. So that'll be multiplied by 35. So, again, I probably put parentheses here and just put like a times, but dot here is probably better. So I'll do that. I'll type that in. We have 5,000 times, I'm going to do second, and then hit that E button here. E button. E to the parentheses 0.055 times 35. Close off that power, and that's going to be the most money we can make. We can make 34,275. Now that doesn't look that much better. You're like, wait, we already made 34,000 last one. Yes, there's a limit, right? Just because you compound as much as you can doesn't mean that the number is going to go off to infinity. If that was true, people wouldn't let us do this. They'd say, oh, only monthly because it's not fair. But it is still more money, right? I think it's like 150 bucks more. That's 150 bucks we wouldn't have made if we wouldn't have done continuous compounding. So that's still what people do. People that want to make lots of money with their investments, they invest in things that are going to pay continuous compound interest. Things like the stock market can pay continuous compounding. One of the big ones is actually like school loans or house loans. So like real estate loans and school loans, stuff like that. Those are calculated with continuous compounding. So if you're like me, if you have a car loan or if you have school loans or stuff, those are all continuous compound loans. In fact, one of the things you'll see if you go to school, go to college, and you get done, and you have your school loans, and you go look at the websites where you pay them off, you'll see a thing called a loan payoff calculator. And what that is because your loans are doing continuous compounding, where the interest is compounding constantly, every single moment, every day. To pay those off, if you like wrote a check, sent in the mail, or even if you did like direct deposit, it takes time for that to process. And in the time it takes for that check to process, if you paid like all you had left on the loan, well, in that time that it processes, you end up with actually the loan getting a little bit bigger because of that continuous compound interest. So what you have to do is you actually have to find out how much do I pay now, so that by the time it's done processing, I've actually paid off the whole amount. So like if you had $1,000 left on your loan and you sent $1,000 check right now, you pay off that $1,000, but it may have made like $5 in interest by the time the check paid off. And so you pay off $1,000 and you still have a $5 loan left over. So you do the loan payoff calculator. It says, okay, pay $1,005 now. Because it says 1,000, but if you pay 1,005, by the time it processes, you'll pay off the whole amount. And that's why they have that. It's a thing. Continuous compounding is pretty ubiquitous. If you borrow money from a bank, they're probably paying continuous compound interest. Cars, houses, all that kind of stuff is continuous compounding. So. Now, that being said, I know that makes it kind of sound depressing because when you think about borrowing money, it's not very much fun. But if you're investing money, if you're actually out there investing money, that can be a great way to grow your wealth, to make more money for things like retirement and stuff, is to invest in accounts that do grow with continuous compounding. So because we've been talking about continuous compounding investing, I really like to kind of just share, this last page. This is something that I think is really handy to have, good knowledge to have, especially if you're someone going to college. You're probably thinking about a full-time career when you're done with school. And so you're going to be thinking about, in the long run, retirement and how you work with your money. I know myself, I did the same thing when I was about done with my degree. I was really looking into, money advice and stuff like that. So I'm going to share this page. One thing I found when I was getting ready to graduate, I read a whole bunch of different books about finance because I wanted to be more knowledgeable about it. And I found that a lot of them said the same thing. And I'm not the only person that thought that. There's actually a guy who's way more famous than I am. I'm not famous at all. Who actually did the same thing. He was reading a bunch of books and said, hey man, these all say the same thing. They all kind of say the same advice, just in different ways. And someone said, well, that's true. You should make like a little cheat sheet, So he did. He actually made this 3x5 note card, and it went viral. So you can look this up. And his name's Dr. Harold Pollack, and he made this little index card, and he put like 8 things that were good advice that he thinks that show up in all those books. It's been on NPR. There's been featured on podcasts with Freakonomics. So you can look that up. You can Google this. Disclaimer: neither him nor I are finance experts. He actually, I think, ended up working. He was working in the medical field, like in the on the back end with like how the accounts and stuff like that. So you might have a little more financial experience than I do, but I think these are good advice. And like I said, he said, and I think this is true. This will be the same advice you kind of see anywhere you look up. So I'm just going to run through these real quick just to show you what they are. You can Google these terms and look at them. But first off, if you work for a business that has some kind of employee match, some retirement thing, you always want to max that out. The idea is like if you put $1,000 in, then your work also puts $1,000 into the savings account for your retirement. A lot of times they're 401ks. So I always want to max your like 401k or whatever employee contribution program they have. He recommends using inexpensive, well-diversified mutual funds. A mutual fund is kind of a collection of different stocks and bonds, so you're not just investing in one thing. He specifically recommends the Vanguard Target funds. These are basically designed for retirement. What they do is you pick what date you want to retire. So like me, I'm going to retire in about 30 years. So in about 2050, 2055, whatever, I'll retire. So I actually do have some Vanguard Target funds I've bought into and I'm buying into. I buy the 2055 ones. And what they do is right now they have more risky investments because I'm young. I've got 30 more years of working most likely. And then as I get older, they'll sell the risky investments and buy safer investments. And then as you're getting closer to retirement, your investments will be safer and safer and safer. Then it won't be as likely to fluctuate, go up and down. Some stocks and stuff can really go up and down, so that's great. Because when you're young, you have time to grow over a long haul. But if you're old and you're about to retire, you don't want them to drop really fast all of a sudden on you. So this is just a good advice. I think these are kind of a good tool for someone who's going to buy and hold for the long run and retire. So it's something where you don't have to keep track of it. You just you buy it and let it sit, and then when you retire, the money's there for you. Next thing he says is never buy or sell an individual security. What he's talking about with security, that's another name for stocks. So he's saying, don't buy just one company's stock. It's not a good thing to do. There's the big like story anecdote is that back in the day there was this company called Enron. Some of you probably heard of it. They were really big. Everybody was really excited about them because they're making lots of money. And so people were putting their whole life savings in just Enron stocks. So they went out and bought a bunch of stocks, and their whole retirement was tied up in it. And then someone found out that there was an accountant who was lying, and the company wasn't making nearly as much money as they said they were. So everybody all decided, I don't want to have any Enron stocks, and they all tried to sell them at the same time. The stock's value plummeted. And there are people who lost their life savings because of this company Enron and what they're doing, that they're lying. And so because they had all this investment in just the one company. So when you buy into just one company, the problem is you never know everything that's going on with that company. The person selling you that stock, they probably know more than you do about it. Even if you've done your research, there's the reason why they're selling most of the time. So it's always dangerous to buy and sell just a single company like that. That's kind of, I think, why he mentions mutual funds. Usually that's a collection of like several companies. So you're not just buying ownership in one company. You're not hoping that one company does well. That's kind of, more of like a gamble when you do that. He says save 20% of your money, which I think is a great idea. I know that's difficult though. Not a lot of people can actually like save 20% of what they make. I'd say set a target. Maybe you can't set a 20% target, but maybe you can do 10%. Maybe you can't do 10%, but you can do 5%. Maybe you can only do 2%, but save part of your money every month. Try and figure out how to cut back your spending. So every month you're just getting some of that money put into some kind of savings account for the long run. So things, big expenses that are gonna come up like medical expenses or having to replace a car or emergencies and stuff like that. It's good to just have some savings that are good building up and over time and being ready for that. Just try and think about how you can do that, how you can set aside money each month. Pay your credit card balance in full every month. So it's never a good idea to carry a balance on your credit card because credit cards charge ridiculously high interest. A lot of times it's 20, 25, even 30 or more % interest. All the problems we've been doing so far, we've been doing like 5% interest. You saw the compound interest making that shoot up. Well, if you have a credit card at 25% interest, it's basically doing that, only shooting up faster, and it's against you. It's making you pay a lot more money. If you're stuck with some credit card debt and you can't pay it off, go get a personal loan from the bank. Because a personal loan from the bank is like 8%, and that's still way less than the 25, 30% credit card is charging you. So you can save a lot of money just by like borrowing some money from the bank for the short term, pay off your credit card that month, and then pay off the bank, and then save money on interest. So credit cards are terrible about really, letting you run up a big bill and then pay tons of interest money. You never want to carry a balance on a credit card if you can avoid it. Maximize tax advantage savings. The government wants you to save up for things like college and retirement and your first home. And so they actually provide different ways to do that. And what they do is they actually make it so that if you invest in these kinds of accounts, you don't have to pay as much taxes. Sometimes you don't have to pay any taxes. So there's IRAs, there's Roth IRAs, SEPs, a 529. 529 is what I actually use. It's a way to save for college. So if you have kids and you want to save for their college, you can take your money, and you'll pay taxes on the original money, but you'll put it in this 529 account, and then it will grow and get bigger and bigger and bigger. And you don't have to pay any taxes as it grows. And if you pull it out and pay for your kid's college, you don't have to pay any taxes on how it grew. Versus if I just go buy a stock or a mutual fund, just regular, buy it, and it gets more valuable, and then I sell it and I make a profit, I have to pay taxes on that profit typically. So using something like a 529 allows you to avoid some taxes, and it's a legal way to avoid taxes. It's a government, hey, I want you to help you save, so I'm going to let you not pay taxes. So try and do tax advantage savings. So try and invest in ways where you're not going to pay as much taxes. Pay attention to fees. So mutual funds, because they're a collection of different stocks and stuff, they have to be managed. Usually there's a person or a computer sitting there and picking out which stocks to buy and how many. Those people that do that, if you have a person that does that, they usually get paid really well. Well, their money that they get paid comes out of your money that's invested there. And so what he's saying here is, avoid the ones where you're paying a big stockbroker 6 digits, all this money out of all your investments. Look for ones that have low fees because they're using like a computer to do it instead of a person. And like the Vanguard target funds, stuff like that, it would be like probably lower fees because they use like a computer or they have a system. They're not paying someone like 6 figures. So watch the fees. And a lot of investments will have high fees because they pay some big shot, broker. And those are the ones you're probably not going to make as much money on because the fees eat out of your bottom line. Next one, he talks about financial advisor because, of course, this is a lot to take in. So I don't know about you, but this is a lot for me even. And it's a good idea to have some kind of advisor. The problem is a lot of financial advisors are just salesmen. They're just trying to sell you investments, right? And if you go talk to one that's not, honest or trustworthy, you can end up, buying into stuff they tell you is good. In the past, a lot of people have bought into things because of advice of financial advisors, and then they've lost money, lots of money. So make sure you've got someone that you can trust. There's a reason you can trust them. They talk about the fiduciary standard, and basically this is a standard saying that the person works for you and not for the companies that are selling these investments. So that's the big thing. They don't get a cut of the sales of those investments. They get paid by you typically. And so it's better for you to pay the person a set fee than to find out like, oh yeah, they're actually getting kickbacks or getting paid from these big companies that want you to buy their investments. So watch your financial advisor and make sure that they're working for you. Last one here, he put on there, promote social insurance programs to help people when things go wrong. I think the idea here is that if there are no safety nets, then people can get in trouble even when they try and do all this stuff. Sometimes you have medical emergencies. Sometimes your house burns down. You have a pandemic. Things happen that just no matter how prepared you were, they can wipe out your savings, wipe out your situation. And having social insurance programs, things where food banks, stuff like that, that actually gives us a safety net where we can kind of help people out. And if we all help keep those going, if we're all working and doing things like helping the food kitchen and stuff like that, then when other people fall, they have someone to help them. And eventually, if we have problems, then someone is there to help us out. So, look at how you can help others out. What can you do to be part of the solution? What can you do to help others? Because if you help, if everybody helps, then we all get help when we need it. So, a little bit of a soapbox lecture there. I just, I think it's good advice. And I like to put this in here after we talked about investing. Big idea is if you start investing when you're young, you can use that compound interest, and it gets to grow and grow and grow up that steep curve. And so you want to make sure you're doing this right away. As soon as you get your first full-time job, as soon as you're done with college and you're working in a career, you want to make sure you're investing and getting ready for retirement. You can borrow money for a house, you can borrow money for a car. When it comes to like retirement, you can't borrow money for retirement. So you want to make sure that you're putting money away and having that ready for when you do retire. They say that there are people that will sacrifice their retirement for pay for their kids' school, and then they find out later that doesn't work out so good because, you know, when you go to retirement, if you don't have money, you can't retire. But if your kid didn't have money for school, they could have borrowed money for school and paid it back later. So you always got to think about, retirement is a big deal. You need to make sure you're going to have money for retirement when you do that. So, all right, I'm done with my soapbox. I'm done with the section. I'm done with exponential functions. Next time, in the next set of notes, we're going to talk about what the opposite of these are. What would be the inverse of an exponential function? I'll see you then.